Electricity is one of those things that feels ordinary only because we have learned to stop being surprised by it. We flip a switch and light appears, we plug in a device and it comes to life, and because it works so reliably, we assume it must be fully understood. But when we slow down and ask what is really happening, the confidence fades quickly. One electric charge influences another across empty space, without touching, without anything visible traveling between them in the way everyday objects interact. We say there is an electric field, and this helps us calculate forces and design circuits. But saying field does not dissolve the mystery. It simply gives us a precise way to talk about it. The field is not something you can point to or hold, yet it carries energy, momentum, and information. This is where electricity becomes a lesson in how physics actually works. Science is not a collection of comforting explanations. It is a discipline that describes nature as honestly as possible, even when that description feels strange. Electricity behaves with perfect consistency according to laws we can test again and again, yet those laws rest on ideas that resist simple mental pictures. That tension is not a problem to be fixed. It is the heart of discovery. The educational power of this way of thinking lies in separating understanding from familiarity. Many people believe that to understand something it must feel intuitive, but electricity proves otherwise. We understand it well enough to predict its behavior with extraordinary accuracy, to build technologies that depend on it absolutely, and to trust it with our lives, even though we cannot say what it really is in any ordinary sense. This teaches a crucial lesson. Understanding in science means knowing how nature behaves, not forcing it into metaphors that make us comfortable. When we confuse naming with understanding, we stop asking questions. Calling something a field, a force, or a particle is useful, but it is not the end of thinking. It is the beginning. Electricity reminds us that the universe does not care whether our brains find it intuitive. It only cares about consistency. Education succeeds when it trains the mind to accept this, to work with precise descriptions even when mental pictures fail, and to resist the temptation of shallow explanations that feel satisfying but explain nothing. There is also a deeply motivating message hidden in this honest approach. Admitting that electricity still baffles us at a fundamental level is not a weakness. It is a strength. It keeps curiosity alive. It reminds us that progress does not come from pretending the mystery is gone, but from respecting it enough to keep probing. Every advance in physics has come from someone noticing that a familiar explanation was not really an explanation at all, and daring to ask what was missing. Electricity teaches us that it is possible to move forward without complete answers, that usefulness and mystery can coexist, and that uncertainty is not the enemy of knowledge, but its engine. This mindset extends far beyond physics. In any field, growth depends on the willingness to say, I know how this behaves, but I don't yet know why, and to treat that gap not as failure, but as opportunity. Electricity, in this light, becomes more than a force that powers machines. It becomes a lesson in intellectual honesty. It shows that real learning is not about closing questions, but about asking better ones, and trusting that careful thinking, precise observation, and curiosity will carry us forward, even when the universe refuses to explain itself in simple terms. Electricity feels so ordinary that it rarely inspires wonder, yet the moment we stop and ask what it actually is, we find ourselves standing at the edge of a deep and unresolved mystery, and this is precisely why it remains such a powerful teacher of how physics truly works. We can describe electricity with remarkable accuracy. Charges attract and repel, currents flow, fields fill space, and equations allow us to predict outcomes with astonishing precision. We know how to calculate the force between two charges, how energy moves through a circuit, and how electromagnetic waves carry information across vast distances. None of this is vague or uncertain. It works every time we test it. Yet the confidence dissolves when we ask the seemingly simple question of how one charge influences another across empty space. There is no physical rope connecting them, no tiny gears turning between them, and no substance we can point to moving from one place to another in the way our everyday experience would suggest. We say there is an electric field, but that word does not make the mystery disappear. The field is an abstract structure that exists everywhere in space, stores energy, and transmits influence, yet it has no texture, no color, and no obvious mechanical explanation. Calling it a field is not an explanation in the everyday sense. It is a precise description of behavior that allows us to calculate what will happen next. This reveals a crucial educational lesson. Science is not about turning the universe into a comfortable story, but about describing it honestly, even when the description feels strange. Electricity shows us that understanding does not mean eliminating mystery, but learning to work within it without self-deception. The universe does not promise us explanations that fit human intuition. It offers consistency, and consistency is enough to build reliable knowledge. This is where electricity still baffles physics, not because it refuses to obey laws, but because the laws themselves do not answer the deeper why questions our minds naturally ask. Yet this bafflement is not a flaw, it is the engine of progress. If we pretended that naming the field was the same as understanding it, curiosity would die. Instead, the unresolved nature of electricity keeps inquiry alive, reminding us that every concept we use is a tool, not a final truth. There is something deeply motivating about this honesty, because it frees us from the false expectation that learning must end in certainty. We can calculate, predict, and build with electricity while still admitting that its fundamental nature remains elusive. This teaches intellectual humility, showing that even our most successful theories are approximations, maps rather than territory. At the same time, it builds confidence, because it proves that we do not need perfect philosophical clarity to understand how the world behaves. Electricity works whether or not we feel comfortable with it, and our task as learners is not to demand that nature explain itself in familiar terms, but to listen carefully to what experiments tell us and to follow the logic wherever it leads. In this way, electricity becomes more than a physical phenomenon. It becomes a lesson in how to think, how to learn, and how to remain curious in a universe that does not owe us simple answers. When we examine electricity more carefully, the confusion it creates is not a sign that physics has failed, but a signal that we are asking deeper questions than our everyday intuition is prepared to answer. We can track electrons moving through a wire, measure voltages, calculate currents, and design systems that depend on these calculations with complete reliability. Yet even here, the moment we try to form a simple picture in our minds, the story begins to fall apart. Electrons do not flow through a circuit the way water flows through a pipe, even though that analogy is often used to make things feel familiar. The forces that move them are not pushes from behind, but influences that exist throughout space at once. An electric field fills the region around charges, shaping motion long before anything visibly happens. And when a circuit is completed, changes propagate through that field at incredible speed. This means that electricity is not a thing traveling from one point to another in the way everyday objects do. It is a coordinated behavior of fields and charges that only makes sense when described mathematically. This realization is unsettling because it strips away the comforting idea that understanding requires a picture we can visualize. Instead, electricity teaches us that reality can be precise without being picturable. Education often fails when it tries to protect intuition at the expense of accuracy, but electricity refuses to cooperate with that approach. It demands that we accept abstraction, that we trust consistent rules even when they do not fit common experience. This is not a weakness of physics. It is a strength because it shows that knowledge is built on evidence and logic rather than on what feels right. The baffling nature of electricity is a reminder that learning is not about making the world simpler than it is, but about training the mind to handle complexity without confusion or fear. There's also a powerful motivational lesson hidden in this honest confrontation with mystery because it reshapes how we think about progress and understanding. Many people believe that once something is useful, it must be fully understood, but electricity proves that usefulness and mystery can coexist for a very long time. Long before anyone had a deep theoretical account of electric phenomena, people were already harnessing it, experimenting with it, and building technologies that change the world. This tells us something important about how knowledge grows. We move forward by refining what we can measure and predict, not by waiting for perfect explanations. The unresolved questions surrounding electricity are not embarrassing gaps to be hidden. They are open doors inviting further exploration. Admitting that something still baffles us is not an admission of defeat, but an expression of intellectual honesty. It keeps curiosity alive and prevents science from turning into dogma. This attitude extends far beyond physics. In any field, progress depends on the willingness to say, "This works, but I don't yet fully understand why," and to treat that gap as motivation rather than failure. Electricity teaches us to respect the difference between description and explanation, between models that work and stories that merely feel satisfying. It encourages humility because even our most successful theories have limits, and confidence because those limits do not prevent us from learning, building, and improving. By embracing the strangeness of electricity instead of trying to explain it away, we develop a mindset that is resilient, curious, and open to revision. This is the kind of thinking that drives discovery, not only in science, but in every serious attempt to understand the world. Electricity becomes truly fascinating when we realize that its greatest success lies not in how comfortably we can imagine it, but in how reliably it behaves despite refusing to fit into simple pictures. At a fundamental level, electricity forces us to abandon the idea that understanding must always feel intuitive. We are used to thinking that causes must touch effects, that forces require contact, and that motion happens because something pushes something else. Electricity violates all of these expectations. Charges influence one another across empty space, and that influence exists even before anything visibly moves. The idea of an electric field helps us calculate and predict this behavior, but it does not explain it away in the everyday sense. The field is not a material substance, yet it carries energy and momentum and determines how matter behaves. This forces us to confront a difficult but essential educational lesson. Reality does not need to match our mental pictures in order to be real or understandable. What matters is consistency, testability, and predictive power. Electricity follows precise rules that never fail, even though those rules describe a world that does not resemble our everyday experience. Learning to accept this changes how we approach knowledge. It teaches us to stop demanding that nature explain itself in familiar terms and instead to focus on what experiments actually reveal. This shift is uncomfortable at first, but it is also liberating because it frees us from the false idea that confusion means ignorance. In truth, confusion often means we are touching something deep. Electricity shows that abstraction is not a weakness of science, but one of its greatest strengths, allowing us to describe reality accurately even when intuition falls short. As we go deeper, electricity also teaches us something profound about the limits of explanation and the danger of mistaking words for understanding. When we say that charges interact through fields, it is tempting to believe that the mystery has been solved, but this is only a partial victory. The word field organizes our knowledge and makes calculations possible, but it does not answer why the field exists or why it behaves the way it does. This is not a failure of science. It is an honest stopping point. Every explanation in physics eventually rests on principles that are accepted because they work, not because they feel inevitable. Electricity reminds us that explanation is not an infinite ladder, but a structure built on experimentally verified foundations. Recognizing this prevents intellectual laziness. It keeps us from thinking that attaching a technical label to a phenomenon means we have truly understood it. Education often goes wrong when it replaces curiosity with vocabulary, encouraging students to repeat terms instead of asking questions. Electricity resists this kind of shallow learning. It constantly exposes the gap between describing behavior and understanding cause, and in doing so, it keeps inquiry alive. This is deeply motivating because it shows that there is always more to explore. The unanswered questions are not signs that physics is broken. They are evidence that it is alive. They remind us that knowledge is provisional, refined over time, and always open to deeper insight. By learning to be comfortable with this, we develop intellectual honesty and resilience, qualities that matter far beyond science. Ultimately, the way electricity continues to baffle us offers a powerful lesson about how progress actually happens. Advancement does not require complete understanding. It requires careful observation, disciplined reasoning, and the courage to admit uncertainty without surrendering rigor. We can build technologies, test theories, and expand knowledge while still acknowledging that the deepest nature of electricity remains elusive. This balance between confidence and humility is one of the most valuable outcomes of scientific thinking. Electricity shows us that it is possible to know a great deal without knowing everything, and that demanding absolute clarity before moving forward would stop progress entirely. This lesson applies to every area of learning in life. Growth depends on the willingness to work with incomplete knowledge, to revise ideas when evidence demands it, and to resist the temptation of oversimplified explanations. Electricity becomes a metaphor for learning itself, powerful, precise, and reliable, yet fundamentally deeper than our intuitions. By accepting its strangeness rather than trying to explain it away, we cultivate curiosity instead of complacency, understanding instead of illusion. In this way, electricity is not just a force that powers our world, it is a reminder that the most meaningful knowledge comes from respecting mystery, trusting evidence, and remaining brave enough to keep asking questions even when the answers are not yet within reach. Electricity continues to captivate because it reveals a universe that operates according to principles far removed from everyday experience, and yet those principles are consistent, predictable, and astonishingly useful. When we trace a current through a wire, we witness a behavior that can be precisely measured, calculated, and harnessed to light homes, power machines, and transmit information across continents. We see electrons moving, we measure voltages and currents, and we can predict outcomes with almost absolute certainty. But if we attempt to form a mental picture of what is actually happening, the simplicity we crave disappears. The motion of electrons is guided by fields that exist throughout space, exerting influence without any obvious mechanism that aligns with ordinary intuition. We speak of forces, of potential differences, and of fields. Yet these are abstractions, tools that allow us to describe and manipulate electricity rather than concrete objects we can see. This is what makes electricity both maddening and inspiring. It functions perfectly according to rigorous rules, yet those rules defy the way our senses expect the world to operate. This contrast between predictability and mystery is a profound lesson about learning itself. Education often aims to make complex concepts feel familiar, but electricity teaches that reality does not owe us familiarity. Understanding does not require comfort. It requires engagement with evidence, careful reasoning, and the patience to follow logic, even when it challenges intuition. By confronting this strangeness, we learn to think critically, to accept abstraction as a legitimate form of knowledge, and to appreciate that mastery is not always about picturing phenomena clearly, but about describing them accurately and consistently. The apparent contradictions in electricity, the gap between tangible observation and abstract explanation, demonstrate that science progresses not by eliminating mystery, but by developing ways to work reliably within it. Beyond its practical applications, electricity teaches a deeper lesson about the nature of questions and answers in science. Saying that an electric field exists is useful, but it is not the same as knowing why the field exists or why it behaves the way it does. The ability to predict behavior does not equate to eliminating fundamental uncertainty. This distinction is vital because it separates the reliability of scientific knowledge from the need for metaphysical satisfaction. Many learners believe that comprehension requires a fully formed picture, but electricity disproves that notion. We can achieve extraordinary precision in prediction and technological control while still acknowledging that the underlying mechanisms remain conceptually elusive. This is an empowering realization because it frees us from the impossible demand that everything must be intuitively obvious before we can act. Science, and by extension life, often requires that we make progress with partial understanding, trusting in consistent evidence while remaining open to refinement. Electricity exemplifies this balance perfectly. It allows us to harness enormous power, to transform society, and to explore deeper principles, all while leaving space for curiosity, wonder, and the persistent questions that drive inquiry. It demonstrates that unanswered questions are not obstacles but catalysts, fueling the ongoing pursuit of knowledge and innovation. The strangeness of electricity is not a deficiency. It is an invitation to think more rigorously, to question more deeply, and to cultivate a mindset that thrives on exploration rather than superficial certainty. By embracing these unresolved mysteries, we learn that real understanding grows not from comfort, but from courage, persistence, and honesty in confronting the unknown. Moreover, electricity highlights an essential truth about the relationship between observation, abstraction, and reality. What we measure, currents, voltages, fields, can be manipulated, calculated, and verified repeatedly, yet the underlying nature of what is being measured resists visualization. Electrons are real and their effects are tangible, yet the invisible structure guiding their behavior is intangible. Intangible in a way that challenges our natural instincts about cause and effect. This teaches us a powerful lesson about abstraction, that it is not a flaw in human thinking, but a fundamental tool for understanding a universe that does not conform to human-scale intuition. To study electricity effectively, we must trust in mathematical descriptions and experimental evidence, even when they contradict the feel of common experience. This requires discipline, patience, and the willingness to operate within models that are partially conceptual, partially formal, and partially experimental. The motivational value of this approach is enormous. It shows that progress does not demand perfect comprehension of every mechanism. It demands that we learn to engage consistently and rigorously with what can be measured and tested. Electricity thus becomes both a practical tool and a profound teacher. It instructs us in how to think systematically, to rely on evidence, and to maintain curiosity and humility in the face of deep, unresolved questions. It is a reminder that knowledge is not the same as visualization, that certainty is provisional, and that mastery often comes from the interplay between understanding behavior and acknowledging the limits of intuition. Finally, the persistent mysteries of electricity offer a lesson that extends far beyond physics. They reveal that intellectual growth is powered not by immediate clarity or intuitive satisfaction, but by the willingness to confront strangeness with curiosity and rigor. Electricity works predictably and reliably, even when we do not fully comprehend its underlying nature, and this paradox is profoundly encouraging. It teaches us that confidence can coexist with humility, that action can proceed without complete understanding, and that exploration is often more valuable than certainty. By grappling with the abstract, counterintuitive, and elusive qualities of electricity, we develop mental habits that apply to every field of inquiry: patience in the face of ambiguity, reliance on evidence over comfort, and the courage to ask questions that do not yet have simple answers. In this way, electricity is more than a force that powers machines. It is a teacher that cultivates resilience, critical thinking, and creativity. Its baffling nature reminds us that mystery is not an obstacle to knowledge, but a guide, and that learning is not about erasing confusion, but about developing the tools to navigate it. The lessons of electricity encourage a mindset that thrives on curiosity, embraces rigor, and respects the profound subtlety of reality, showing that even phenomena we take for granted every day hold the potential to transform how we think, how we learn, and how we understand the world around us. Electricity is one of those phenomena that we interact with constantly, yet it remains fundamentally mysterious. And it is precisely this combination of familiarity and strangeness that makes it such a powerful teacher. At first glance, electricity seems simple. Flip a switch and a light comes on, plug in a device and it works, or measure a voltage and predict a current, and everything behaves reliably. We can calculate its effects, design circuits, and transmit signals over thousands of miles, all with extraordinary precision. Yet if we pause and ask what electricity really is, the simplicity vanishes. Charges influence one another across space, seemingly instantaneously in some senses. And yet the underlying mechanism is not like anything in our everyday experience. There is no substance flowing visibly from one place to another in the way water flows through a pipe. Instead, what we call an electric field exists throughout space, exerting influence, carrying energy, and guiding motion, yet it cannot be touched or seen in a direct way. Calling it a field is not a full explanation. It is a precise way of describing behavior that allows us to predict outcomes. This is a critical lesson about learning and understanding. The universe does not need to make intuitive sense for its laws to be consistent, testable, and reliable. In this way, electricity teaches us that mastery is not about making the strange familiar, but about working rigorously and honestly with what can be measured and tested. The mystery is not a flaw in science, but a sign that we are engaging with something profound. By confronting the strangeness of electricity head-on, we train ourselves to think critically, to reason clearly, and to accept that evidence and consistency matter more than comfort or intuition. The second lesson electricity offers is that progress does not require complete understanding. Humanity has been using electricity long before we had a full theoretical framework to describe it. Early inventors and experimenters could harness currents, power devices, and communicate through telegraphs and simple circuits without needing to grasp the deep principles that govern fields, charges, and electromagnetic interactions. This teaches a powerful message about learning and innovation. Useful knowledge and understanding are not the same thing. We can act successfully in the world without knowing every underlying detail. And in fact, the pursuit of application often drives deeper discovery. Electricity illustrates that unanswered questions are not failures. They are invitations to think, experiment, and explore. Recognizing this helps cultivate humility while also encouraging curiosity, showing that it is not a weakness to admit that we do not yet understand something fully. Rather, it is an opportunity to engage more deeply and refine our thinking. The fact that we can rely on electricity's behavior while still acknowledging that its fundamental nature remains elusive teaches us to value precision, observation, and reasoning above mental comfort. And it shows that learning is an ongoing process rather than a completed product. By embracing the coexistence of mystery and utility, we develop a mindset that balances confidence with inquiry and action with reflection. Third, electricity emphasizes the importance of abstraction in understanding the world. Unlike everyday objects, which we can see, touch, and intuitively comprehend, electricity operates through invisible fields and forces that can only be described mathematically. Electrons move in ways that defy simple visual analogies, guided by potentials, fields, and interactions that are imperceptible to our senses. Accepting this requires training the mind to trust in evidence and mathematical reasoning, even when intuition fails. This is a profound educational lesson because it teaches that reality is not obligated to match our mental images or intuitive expectations. True understanding often comes from engaging with structures that are abstract and intangible, yet consistent and predictable. Fields, voltages, and currents are not illusions. They are representations of reality that allow us to interact with it effectively. Learning to operate with such abstractions fosters intellectual flexibility, critical thinking, and resilience, skills that are broadly applicable beyond physics. Electricity, by defying simple visualization, trains the mind to work with complexity and uncertainty without losing precision or rigor. This ability to handle abstraction is a cornerstone of scientific thought and a model for disciplined learning in any domain. It demonstrates that knowledge is not defined by familiarity or comfort, but by clarity, logic, and empirical consistency. A fourth insight that electricity provides is the distinction between description and ultimate explanation. When we describe an electric field, we can predict exactly what will happen to charges placed within it. We can manipulate circuits, design sophisticated devices, and explore electromagnetic phenomena with confidence. Yet describing behavior does not equate to answering the deeper question of why it exists or why it behaves according to the specific rules we observe. This gap between description and fundamental explanation is where true curiosity thrives. It reminds us that knowledge is provisional and layered. We build models that work within observed constraints, while always being open to deeper insight as new evidence or ideas emerge. This principle is motivational because it liberates us from the impossible expectation that understanding requires total comprehension.